Hello guys, we're going to be covering section 3.11, which is hyperbolic functions. So I'm just going to get out and say it. Hyperbolic functions are probably something that, like, if I'm honest, I don't really remember. I'm going to be like, when I look at this, I'm just like, this thing again. And I don't view it as something that's, very heavy in what I do. Like, as someone who's done a lot of math lately in my life, I don't really see these appear up too much often. I see that I see them appear in like they have engineering applications and a lot of applications. But what I want you to go about when you watch through this video, what I want you to keep in mind is that this section is important, and you should know it, of course. But would I want you to waste a lot of time on it? Waste a lot of time trying to understand this section? No, but it's the important part of this section right here is seeing it, because if you ever see it in real life, then I would want you to be able to say, okay, I've worked on this before, I have an idea what this is like, and it should like kind of click in if you ever have to do the work based off these functions again. So this isn't to say to skip the video or anything, because it's so important, and it's still, honestly, anytime you get into weird math and you more work with something that's very unintuitive, takes a while for you to like just digest, then it definitely helps you become a better person, at least a better math person. So now, I talk about these functions a lot now, so what do they really mean? Hyperbolic functions are basically just like fancy trig functions. So we have, for the trig functions, we have sine, cosine, tangent, cosecant, secant, and cotangent. For hyperbolic functions, we basically have, hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cosecant, and, so on. Typically, when you say them is kind of different. So, if you see sine, you don't say sin of x, you usually just say sine. For cosine, you just say cosine. You don't really say cos. In terms of hyperbolic functions, you might do that more often. So, you could say this is hyperbolic sine of x. Or you could say, for cosine, it could be like cos of x. Sometimes sine of x, hyperbolic sine is also called sinh or tanh. I don't know. I don't think that tanh is a thing, but hyperbolic tangent. But that's kind of just go about the names of them. But anyways, so if you look at, hyperbolic sine of x, or, sinh of x, that's defined to be e to the x minus e to the minus x divided by 2. And hyperbolic cosine is going to be defined pretty similarly, where instead of it's going to be the minus, it will be the plus. So it'll be e to the x plus e to the minus x divided by 2. And you might be asking, why are they defined this way? Just a quick side note, if you do want to learn more about these kind of things, is these are the real parts and imaginary parts of I'm more used to seeing stuff with this definitions versus actual hyperbolic functions. If you want to learn more about kind of where they come from, you could look up the complex version of cosine of z, or really where cosine of z is cosine of a plus bi. So you can define the trig functions in terms of complex numbers, and when you do that, you can take the real part or the imaginary part, and you basically get these hyperbolic functions. So that's kind of where I see them. And that's because they're defined literally in this way, but in terms of x, but instead of x anymore, they're defined as z, e to the z. All right, so done for the tangent for right now. Let's just get into the nitty gritty. I just wanted to kind of give you guys some intuitive idea and give you a bit of story and background of these functions. All right, because honestly, it's just going to be a lot of this section is just, knowing the details. So assuming you just copied everything down, hyperbolic tangent of x is equal to sinh of cosine of h. And they're all basically defined pretty similarly to their just trig counterparts. Hyperbolic cosecant is just going to be one over hyperbolic sine, and so on. So basically kind of the same thing that I just said right here. Hyperbolic functions have a similar relationship as trig functions, and they have applications in the description of ocean waves and bridges and so on. So they basically have some applications in real world engineering. Frankly, I'm not an engineer, so I don't really know them. I guess a hanging wire is pretty good, I guess, because it's not very like a parabola. But let's do the graphs. So the graph on the left hand side is going to be sinh of x. So remember that's going to be e to the x minus e to the minus x divided by 2. So this is odd. And you note that this looks like, x cubed, or like, x to the fifth. It looks like, like a polynomial degree of like, with some odd power degree. But really, this is going to grow faster or decay faster than any polynomial because they're exponential. So you're going to have like exponential growth. And, hyperbolic cosine is going to be basically, going to be like this kind of like U shape right there. So kind of like what would happen if you just take, x squared or like, x to the fourth and so on. When you look at these functions, as you increase the power, they actually get like flatter and flatter. And basically what it's going to happen is like cosh of x is going to be pretty flat around 1. So like, around here it's going to be pretty slim. But, well, around x equals 0, that's going to be pretty like flat. Well, not slim, but it's going to be flat because of these kind of properties. But again, if you don't want to remember these, like, that's fine. If the more important thing is if you could just remember these definitions right here, or at least kind of know them. Like, if you could, like, understand the, the way they're defined in terms of exponentials, then it's pretty easy to work with them. Just like trig functions, there are many identities relating to different hyperbolic functions. Basically just like, you can have more kind of weird identities like you do with trig functions. Each identity can be proven using the exponential definitions above. So basically it's like, okay, you can just, verify these with the exponentials definitions. So the first one is basically just like, well, I'm going to just read them. So the first one is basically just like, sinh is odd. Cosh, even. So odd, even, that's basically just, like cosine squared of x plus sine squared of x, is equal to 1. It's basically that relationship, but now it's just, with hyperbolic functions. Likewise, you can just take this divided by cosh and just get this one right here. And then you have, like the fifth and sixth one, which is basically pretty similar, like, cosine of a plus b is equal to like cosine of a sine of b minus or whatever. I don't really remember the formula. But, again, these are just more identities that you should kind of be aware of. And one of the things I like, the one that's underlined in blue, so the third one, I'd recommend trying to prove it at least using the identities because, while like, it's important to see them and it's important to know them. And again, I'm not stressing that you should waste a lot of time on them, but you should, work on them a bit. So at least try to prove this identity. That way you get some experience working with them. And if you want to go ham, feel free to go harder on the, all of them if you want. The derivatives, because they're defined in terms of exponentials, can also be pretty easily calculated. So like, d of dx of hyperbolic like sine or sinh of x is going to equal to the derivative of the definition. So e to the x minus e to the minus x divided by 2, so the derivative of that. So, derivative of e to the x is just going to be e to the x. Derivative of negative e to the negative x. So that's going to be e to the negative e to the negative x. So, we keep the negative on the outside. It's basically just a constant. E to the negative x. That's an exponential, so you keep it the same. And you multiply by the derivative of, negative x, so it's going to be negative 1. So that's just a chain rule. So then you just get back, e to the minus x. So it's just going to be positive now. So you get e to the x plus e to the minus x divided by 2. But if you remember the definitions that we had above, that's hyperbolic cosine. So this is pretty nice where, hyperbolic functions are derivatives of each other. But actually, like, wait, that was weird. But this is nice in the sense that when you take derivatives of sine or cosine, you usually get some negative out there. But with like sinh and cosh, they're basically like inverses of each other. So the derivatives follow a pretty similar pattern as the trig functions. It's going to be like a slight variation on them, but they, pretty much are like pretty similar. So, like this is basically just a list of tables again. derivative of sinh of x is cosh, derivative of cosh is sinh. This is kind of where, it gets pretty similar. So derivative of tangent, hyperbolic tangent, that's just going to be sec squared or, secant squared of x. Then likewise for all the other ones as well. I think the only difference is that the derivative of secant normally is just secant tangent, but here it's going to be negative. And again, how I said you probably want to do at least prove the third identity. For here, I probably wouldn't really waste your time verifying all of these. You can if you want to, of course. But I would still at least try to prove the one for hyperbolic tangent. At least try to prove that derivative if you have some time. That way you can have an idea of how to work with these functions. And it's pretty nice to work with. Well, at least that way you have some experience, and when you see it again, it's not very annoying. Because these are just functions or derivatives, can behave pretty normally, so we can apply our normal differentiation rules with these functions. So the product rule, the quotient rule, the chain rule, and all that. So if we do an example the derivative of hyperbolic cotangent, of the square root of x. So we're just going to use the formula that we had above. Derivative of hyperbolic cotangent is going to be negative cosecant hyperbolic cosecant square root of x. So remember that this is the chain rule. If you have an outside function, hyperbolic cotangent, inside function, square root of x. So it's going to be the derivative of the outside, so negative hyperbolic cosecant squared, and evaluate at the inside, so at square root of x on the inside, times the derivative of the inside, so times d of dx of square root of x. And then lastly, all I did right here is just simplify. Well, take the derivative and simplify. So let me just kind of indicate right here, it's just the chain rule. So I'm going kind of fast. Just a lot of these details are just kind of I wouldn't want to say they're redundant, but a lot of them are you just kind of end up check them yourselves, and it's not really worth me just saying them, unless I was doing them with you. But I decided to just have them pre-written beforehand. So, one of the things we could do is, inverse hyperbolic functions. We have inverse trig functions. We have inverse exponential functions. We have logarithms. So as hyperbolic sine, hyperbolic cosine are defined in terms of exponentials, we could actually define the inverse hyperbolic functions, but hopefully within terms of logarithms. But again, we first need to kind of talk about them. We need to introduce them. We need some notation. So for inverse hyperbolic functions, to basically behave like regular trig functions, and the only thing is, it's we typically have to restrict the domain sometimes for inverse functions because we need them to be one-to-one. So cosh of x is going to be the one we're restricting. So remember, we need one-to-one for inverse to be okay. So one-to-one to be invertible. This right here is invertible. It's a cubic. If you look at cosh of x, we need it to be one-to-one. So if you look at this y value right here, any y value where that includes a negative number and a positive number, so something less than 0 and something greater than 0, and it's not one-to-one. So we just say x is going to be greater than or equal to 0. So we say basically just f this side is going to be x is greater than or equal to 0. So why are we restricting that domain? Is because we want to know the y value right here, and they're going to give us an x value. And if we we can't give in two y values to get two different x values, so it'd just not be helpful when you define a function. And that's basically the only restriction. So this table right here, or my attempt at a table, crappy rectangle, I guess, not even really rectangle. So we have them defined pretty similarly. Y is equal to sinh inverse of x if and only if sinh of y is equal to x. Likewise for cosh inverse of x. Cosh inverse of x is equal to y if and only if cosh of y is equal to x. And same thing with hyperbolic tangent. And that's basically just kind of definitions that arise from being inverses. And again, this y is equal to greater than or equal to 0 is going to be our restriction basically. Otherwise, these things aren't always defined properly. All right, so kind of like what I was saying earlier, these hyperbolic functions define in terms of exponentials. So we get defined in the inverses in terms of inverses of exponentials, which is logarithms. So, inverse hyperbolic functions, hyperbolic function. You can express inverse hyperbolic functions in terms of logs. So let's do, y is equal to sinh of inverse of x. Oops, I forgot to erase this. So basically, it's, the same kind of thing we're doing. We're going to use the substitution. We're going to do the fact that it's identity. So, if y is equal to sinh inverse of x, then because it's an inverse, we get x is equal to sinh of y. So what we can do right here is just plug in the definition. So sinh of y is equal to, e to the y minus e to the minus y divided by 2. And now we're just going to try to solve for y. So we're going to move that 2 over, get 2x is equal to e to the y minus y, e to the y. Move everything to one side, and we get something like this. All right, so what we're going to do here is basically you're just going to do some stuff that you guys saw in like college algebra or math by calculus or like, your pre-calculus classes. We're basically just doing some fancy algebra. We're going to multiply everything by e to the y, which is going to be greater than 0, so it doesn't change any signs or anything like that. So once we do that, multiply this whole equation by e to the y. Here we get 0. Here we get e to the 2y. Here we get, 2x times e to the y, which is this piece right here. Then we get, e to the minus y times e to the y. That's just going to be equal to e to the negative y plus y. So that's going to equal e to the 0 is equal to 1. So that's how we get this piece right here. But really what that is, e to the y squared minus 2x e to the y minus 1, which is equal to 0. And that's our expression that we have. So we're going to try to do like, this is basically kind of like a quadratic, but our quadratic, it's not really a quadratic here, it's more like an exponential. So, but, we want to do it in terms of a quadratic because it's nicer and it's easier for us to talk about it. So we let u is equal to e to the y. So then we get u squared minus 2x minus 1 is equal to 0. So this is a quadratic now with variable u. We'll just think x is a constant. So this is a quadratic, so we can just use the quadratic formula. A will be equal to 1, b is equal to negative 2x, c is equal to negative 1. And then, you just plug and chug. You plug everything in, you simplify. One of the things is, 4x squared plus 4, you can pull out that 4, and that's how I got this 2 right here. You get x squared plus 1 remaining the square root. You simplify these 2's, and you just get, u is equal to x plus or minus the square root of x squared plus 1. But again, this was a substitution. This is a way just to do the quadratic formula. And so we have, u is equal to e to the y, and e to the y has to be greater than 0. So e to the y would have to equal to x plus x squared plus 1, like the square root of that. And note that here we had plus or minus. Here we only have the plus. This is because, again, we said e to the y is greater than 0, so if it can't be negative, so we discard the negative one. Discard the negative solution. So this relationship right here, take an ln of both sides, and we just get y is equal to the ln of x plus the square root of x squared plus 1. All right, so this was just basically just an exercise, just basically just a bit of calculus to try to prove something, to try to derive something. And so basically what we showed was that, sinh inverse of x, like the inverse hyperbolic function for sine, is equal to ln of x plus the square root of x squared plus 1. And note this is defined for all x. So this is for all x and r. So it's okay, that's pretty nice. And we can do a similar approach to the other inverse functions as well. So we get, sinh of inverse of x, again is defined likewise. Cosh inverse of x is equal to ln of x plus x squared minus 1. And one of the key things we need to note is that x has to be greater than or equal to 1. Otherwise, if you plug in something that's like 0 or something that's not greater than or equal to 1, then what we get is, a negative inside the radical, and we get like a complex number inside the logarithm, which is like undefined for us. And then lastly, what we get for, hyperbolic tangent, like the inverse of hyperbolic tangent, we just get 1/2 ln of 1 plus x divided by 1 minus x. And you'll see, remember that logarithms are only defined when the numbers are like whatever the inside is greater than 0. And this is the case whenever, the inside is greater than 0, when x is between -1 and 1. Likewise, we can also use implicit differentiation to find the derivatives. So instead of actually doing it, I'll actually just kind of like show you what it is. So you basically just have this list again of like, the derivatives of the inverses. So again, it's nothing too complicated. Like again, I wouldn't recommend memorizing these, but knowing that it exists and just seeing them and probably doing a few examples like as you've done in the homework. So like, the derivative of sinh inverse of x, that comes from the ln that we just used. So like, 1 divided by the square root of 1 plus x squared. Likewise with all the other ones. The inverse of hyperbolic cosine, the derivative of that is only defined when the absolute value of x is greater than 1. I think this should be like that. I don't know. I'd have to double check. I realized that was something I was thinking about while I was saying that. I might have paused for a second while I was thinking about it. But I think that might be defined whenever the absolute value of x is greater than or equal to 1, but I'll just look inside just to make sure if you were going to worry about that. So, the derivative, so the only thing you really have to be careful is just, know what the formulas, but also know where they're defined. So, but really, if you plugged in something that wasn't greater than 1 in absolute value, then you would have a negative square root, and that would be an issue. Likewise with, in the derivative of the inverse of hyperbolic secant is also kind of defined pretty similarly as as above, with respect to like of fudge. This is such a word salad. I don't like it. But again, basically what it is just another list of derivatives for you guys to just kind of know. The only one that's kind of gets weird is the last two. So tang inverse of x, the derivative of that, and cos inverse of x. So the derivatives here are a bit weird, where the arguments are the same. So you get 1 minus 1, 1 divided by 1 minus x squared, 1 divided by 1 minus x squared, but they're defined on different values. So, tangent inverse of x is defined whenever x is going to be greater than 1. Well, no, when x is between -1 and 1, or when x is like, in absolute value less than 1. And the cotangent version of that is basically going to be defined everywhere else. So we see that, if x just can't equal 1 or -1, otherwise we divide by 0. But you just have to know that for the derivative of the inverse of hyperbolic cotangent, it's going to be whenever the absolute value of x is greater than 1. Tangent inverse of x is going to be whenever the absolute value of x is less than 1. All right, so this is, all right. So, let's do an example real quick. We want to find the derivative of y is equal to the inverse hyperbolic cotangent of secant of x. So we have to use a chain rule here, where our outside function is, cotangent inverse of x, and our inside function is just secant of x. So we have to use the chain rule. So remember, it's going to be the derivative of the outside. So the derivative of, inverse hyperbolic cotangent is going to be like 1 minus x squared. So 1 minus x squared, but really it's whenever the argument, 1 divided by 1 minus the argument squared. It's really, the x is just the argument here. And the argument here is secant of x, so it's going to be 1 minus secant squared of x. And then we also multiply the derivative of the argument, so times the derivative of secant of x. You can ignore this real quick. This is just, side work that I was doing while I was doing this problem. So the derivative of secant x is just secant tangent. So we just get, for a final answer, secant of x times tangent of x divided by 1 minus secant squared of x. And all the stuff you see on the side is just me simplifying. 1 minus secant squared of x, that's actually just, you have this relationship right here, tangent squared of x plus 1 is equal to secant squared of x. So that tells you that 1 minus secant squared of x is equal to negative tangent squared of x. And likewise, so you could, you go from here to here, and then you could take this as it's equal to this. You could plug in this instead. The tangents would cancel, leaving you with just negative secant divided by tangent. Secant is just 1 over cosine. Tangent is going to be that's basically just cotangent. So cosine over sine. So these cosines will cancel. Maybe you're just negative cosecant of x. But really, you can stop there. I don't really expect you to do more algebra. I just wanted to keep going because I just thought it was pretty interesting. And this is just one of the things I didn't know was that we were going to touch on it in chapter 5. We're not in chapter 5. I don't think you touch on it until like Calc 2, when you learn more about integrals. But this was just surprising to me because when you first learn about the integrals of just regular trig functions, they're not defined in terms of hyperbolic functions. I don't know, which is interesting to me, but that's pretty much it for this section. Sorry I kind of went fast by it. And again, I wouldn't worry too much about trying to understand every detail. Again, it's going to be okay, just make sure to have a reference sheet of all these derivatives of, where the functions are defined, their exponential forms, the logarithmic forms, which again sounds like a lot, but really it's just knowing how to do that. And then I'd probably recommend just probably proving maybe this derivative, if anything, using this definition right here, but it wouldn't really be a pain at all. But just kind of double check that stuff. Maybe do 1 or 2 of these kind of examples just to check it. It wouldn't really hurt. But that's pretty much it for this section. Thank you guys for watching. Like, comment, and subscribe if you like. See you in the next one. Bye-bye.